Bologna, Italy, the 1780s. A medical doctor in a dimly lit laboratory stares at a dead frog. Suddenly, the lifeless leg violently jerks. Dr. Luigi Galvani is startled. He resets his equipment and replicates the test, finding that every time he repeats the conditions, the severed leg kicks as if the animal were still breathing. He notices this reaction happens only when two different types of metal, like copper and iron, make contact with the wet tissue at the exact same time. Curious, slightly hushed. Looking at this anomaly, Galvani concludes he has identified an internal force native to living flesh. He calls it animal electricity. Word spreads rapidly. For a brief moment, the scientific community praises Galvani for demonstrating that animal tissue can generate its own innate electrical current. Just a few towns away, physicist Alessandro Volta hears the news. Initially, he congratulates Galvani, but as he studies the reports, a technical suspicion begins to develop. Volta zeroes in on the necessity of those two distinct metals. He questions if the electrical spark is originating from the frog itself, or if the wet tissue is merely a bridge that allows the metals to interact. By suggesting the frog was a passive pathway rather than a generator, Volta challenged the entire basis of Galvani's theory. Two researchers were now on a direct collision course. Volta formalizes his idea. The moisture in the frog's leg acts as a conductor, a medium that facilitates a reaction between the two mismatched metals. He sends his doubts via letters, but Galvani refuses to yield. He defends his life force theory and dismisses Volta's physical explanation as an oversimplification. The disagreement quickly turns bitter. Across Europe, scientists align into two warring factions, choosing between Galvani's biological magic and Volta's mechanical physics. Volta realized that debate alone wouldn't settle the matter. To prove his point, he had to build a device that created electricity without using any biological matter at all. In the year 1800, Volta gathers his materials. He sets aside the biology and focuses on discs of zinc, discs of copper, and cloth soaked in salt water. He constructs a vertical column with a strict pattern: zinc, copper, and wet cloth. He repeats this sequence, building a rigid stack. When he attaches a wire to the top and bottom, an electric current flows. It doesn't spark and vanish like a static shock. It runs steadily, producing a continuous stream of power. News of the voltaic pile spreads through Europe. Laboratories in London and Paris begin replicating the stack, and eventually Napoleon Bonaparte summons Volta to demonstrate the device, honoring him with a title and a gold medal. For the first time, electricity was a manufactured tool rather than a fleeting natural event. Humanity could now generate, package, and control power on demand. Volta walked away to Vector, while Galvani was remembered as the scientist who got it wrong. But looking at the biological reality, the verdict is more complicated. As medical science progressed, we learned that our brain, heart, and nerves actually do operate on continuous electrical signals. We call this bioelectricity. Galvani was right to identify biological electricity. His error was his belief that electricity could only be produced by living things. Both men were correct in their respective fields, but history favored Volta because his discovery resulted in a machine that changed the world. That first machine had flaws. It leaked, its metals degraded, and its life was short. Other engineers immediately began refining Volta's design for practical use. Over decades, this led to the development of lead-acid batteries, which provided the high-capacity, durable power needed for the first vehicles. This cross-section of a lead-acid battery shows that the core logic hasn't changed. It uses the same alternating plates and conductive medium, simply miniaturized and reinforced for industrial use. This same design lineage leads directly to the dry cells in your remotes and the lithium-ion batteries powering modern laptops and electric cars. We have spent 200 years refining the chemistry, but our modern civilization still relies on the same principle born from that 18th century rivalry: two metals, a liquid, and the flow of power between them.